Hello, and welcome virtually to Brookhaven National Laboratory. I'm Bob Gordon, and I manage the U.S. Department of Energy's office here at BNL. Before you begin exploring this amazing place, let me tell you about the Department of Energy, Brookhaven's owner. The Department of Energy's Office of Science provides most of the lab's $700 million annual budget. We've hired Brookhaven Science Associates, a partnership between Stony Brook University and Battelle Memorial Institute, to run our laboratory, and especially the conduct of world-class science. You probably didn't know that the Office of Science is a world-leading supporter of research in the fundamental sciences. Battelle and Stony Brook are both leaders in science, education, and research. Together, we strive to realize the DOE mission to ensure security and prosperity through transformative science and technology solutions. And you're part of it. Welcome to BNL's Summer Sundays and enjoy the visit.
Hi, and welcome to the U.S. Department of Energy's Brookhaven National Laboratory. Thanks for joining us virtually as we share our groundbreaking research and unique facilities with you online. Today's tour is at the National Synchrotron Light Source II, or NSLS-II, one of the most advanced light sources in the world, funded by the Department of Energy's Office of Science. It's capable of X-ray imaging for new discoveries in many areas of science, including energy security, environment, and human health. We look forward to seeing you in person in the future, but for now, your tour guide is inside and ready to show you around. Let's go!
Hi, welcome to the National Synchrotron Light Source II, or NSLS-II for short. My name is Lisa Miller, and I'm a scientist here at Brookhaven National Laboratory, and I'll be your tour guide for this tour of NSLS-II. I'm standing right now in the lobby of NSLS-II. This is the lobby of a very bright X-ray machine. That's what NSLS-II does. We produce very bright X-rays for doing experiments. Now, you may be familiar with X-rays when you go to the doctor or the dentist office, but the X-rays that we make are very different. They're extremely bright and extremely small beams of X-rays that we shine on very small samples in order to understand their atomic structure. So we want to look down into the very, very small parts of individual atoms and molecules. And that's what the synchrotron does. NSLS-II is one of 5 light sources in the country. They're all sponsored by the U.S. Department of Energy. They're what we call a national user facility, and so scientists will come to NSLS-II from all over the world to do experiments on all different types of materials. They may be studying batteries, they may be studying drugs for diseases, they could be studying solar cells, lots of different things, because in all cases we want to use these X-rays to look into the very, very small components that they're made out of and how they function. Over 2,000 scientists come to the NSLS-II every single year to use the facility, and the reason we can take so many scientists at one time is because we have many experimental stations that we call beamlines, where we collect these beams of X-rays to do experiments. Today we're going to visit 4 beamlines, and I'm going to show you how each of those are a little bit different from each other and describe a little bit about the science that gets done at them. At NSLS-II right now we have 28 operating beamlines, but we're only about half built out. We still have space for up to 60 beamlines for even more experiments to be done in the future. So with that, I'm going to take you onto the experimental floor and we'll take a look at those beamlines. Come along. So the first stop on our tour is the Accelerator Tunnel, which is the heart of NSLS-II. That's where we actually produce those bright X-rays for doing experiments. We produce the X-rays using electrons, and what we do is we take electrons, which are electricity, like you get from your electrical socket. We take those electrons and we accelerate them in a linear accelerator. Once they get up to about the speed of light, we put them into what we call the synchrotron ring, and the synchrotron ring is a storage ring for the electrons where we spin them around in a circular orbit. We can steer them in a circular orbit using magnets, and we have different color magnets in the synchrotron for different purposes. Some of them focus the electrons, some of them steer the electrons, and once they get up to about the speed of light, those electrons spin, and as they turn, they give off energy, and the energy that they give off is in the form of light. And the light that they produce is primarily X-rays. So these beams of X-rays come down what we call a beamline, and at the end of the beamline is where we do experiments. So now we're standing up on the balcony above the experimental floor at NSLS-II, and you can see the entire experimental floor behind me. And what I'd like to point out up here is actually one of the beam lines from a bird's eye view. The beam line starts from the concrete wall, which you can see right there, and the beam line is the dark metal pipe, and inside that pipe is the X-rays, which travel all the way down the beam line, and eventually down just below me is an experimental station where scientists will actually insert their sample and perform the experiments. NSLS-II is a really large research facility. It's almost 3/4 of a mile in circumference. And so one of the best ways to get around the facility from beamline to beamline is by trike. Hop on and join me. All right, so now we're standing at one of our structural biology beamlines called AMX, and it stands for the Automated Macromolecular Crystallography. And at this particular beamline, what we study are proteins and DNA. And what we want to do is we want to use the X-rays from the synchrotron to study the atomic structure of these proteins all the way down to the individual atoms and individual molecules that you see. The reason for that is for something that we call drug design. If you understand the structure of a protein, which is in your body, if that protein is malfunctioning in a particular disease, and you want to know if you want to develop a drug that's going to prevent that protein from functioning or help it to function to cure the disease, you need to understand the protein structure and how it actually binds to the drug. Think of this as a lock and a key, where the lock is actually the protein and the key is the drug. And you need to find the exact key that's going to fit into that protein in order to prevent the protein from functioning or in order to help the protein to function, whichever the case may be in the drug. Now this beamline is it's a highly automated beamline. Back behind me is a robot that you can see, and this robot allows us to study many, many different drugs very quickly and how each one of those will react with the protein. So basically we have our lock and we have many, many, many different keys that we can study the interaction between them using the X-rays and the robot in order to do it very quickly. So one example that's happening nowadays here at this beamline is study of the spike protein in the coronavirus. The coronavirus is the protein that is the cause of the COVID-19, and the spike protein is actually one of the proteins that causes infectivity. And so if we can find a drug that will actually bind to the spike protein and prevent it from infecting a human cell, that will help to treat the disease. And so what's being studied here is the spike protein and many, many different drugs, many of which are commercially available. We're trying to understand whether any of these commercially available drugs will actually be able to function to inhibit the spike protein. And we use the protein crystallography to study at the atomic structure the individual structure of the protein and how it binds, or how that lock and the key fit together in order to prevent infection in coronavirus. So that's just one example, but there are many, many more examples of how structural biology is used. We can study upwards of 500 or more different samples in a given day, so it's a very highly productive beamline for drug discovery. And incidentally, I'll add one more point, that we're very proud to say that more than 90% of the drugs that have been developed in the last 10 to 15 years have used synchrotrons like NSLS-II in order to determine the structure of this lock and this key mechanism together. So that's structural biology. Now what I'd like to do is we'll take you on to our next beamline and take a look at something different. Follow me. Now we're standing at the inner shell spectroscopy beamline, or ISS for short. And the specialty for this beamline is to study catalytic reactions. And the example that I want to give you today is batteries. A lot of work goes on at this beamline to study batteries and how they actually function in real time. I bet that you can imagine that batteries are really important to me. They're really important to you because you want the battery in your cell phone, for example, to be smaller. You want it to charge faster. You want it to hold the charge longer. And you don't want to have to change the battery after having the phone for a few years. So the advantage of the ISS beamline is we can actually study what's happening in the battery in real time. And the advantage to that is we can actually then tweak the composition or the molecules in the battery in order to help it perform faster, or help it to charge faster, help it to hold its charge. And so what scientists will do is they'll prepare all different compositions of batteries, we put them in the X-ray beam, and we compare the function to what the composition is in order to make it better. So that's just one example. Let's move on to the next beamline. This is an X-ray fluorescence microscope beamline, or XFM for short. And as its name describes, what this does is a very, very bright X-ray fluorescence microscope, and that allows us to see the elemental composition of materials. And so one example that I can give you is we can look at the composition of plants. We can stick an actual plant leaf right into the X-ray beam, and we can raster scan it through that X-ray beam, and we can get a picture of all the elements in the leaf. We can learn about the normal elements like carbon and oxygen, nitrogen, phosphorus, but we can also learn about things like contaminants, heavy metals, for example. And that's one particular application that we see being done on this beamline is something called phytoremediation, where scientists are using plants to actually bring heavy metals out of the soil into the plants, and then the plants are taken out of removed and burned, and you can actually recover the metal, but you also remove the heavy metal from the soil. And so in order to do that, the sample gets put into the beam, the X-ray beam will come down, it will absorb into the leaf, and then the fluorescence is given off, so the X-rays will bounce around inside, they'll absorb. The detector will measure the fluorescence, and this detector is able to discriminate the different elements, the arsenic versus the carbon, the oxygen, and the nitrogen. And we get a picture of all of those elements all at the same time. So we can see where that heavy metal was located in the leaf, how much got into there, and how much got out of the soil. Another example of the X-ray fluorescence microscope is looking in the area of cultural heritage, or looking at paintings. We've seen scientists bring paintings here where they want to identify the composition of the paints, which will help to date when the painting was made. We also look at dating the paints for forgeries in these paintings. And a third example in cultural heritage is actually looking at a painting behind a painting. So back in the days, the canvas was very expensive, and so painters would actually paint a painting, and then instead of getting a new canvas, they'd paint a second painting on top of it. And because the X-rays are penetrating, we can actually take a picture with the X-ray fluorescence microscope of the image on top, and then also see the image back behind. So those are just some examples of how the X-ray fluorescence microscope beamline works. Now let's move on to our next beamline. So now we're standing at the 6 beamline, which is a huge beamline. So 6 stands for soft inelastic X-ray scattering, and this type of beamline is used to study things that we call quantum materials. And quantum materials are these next generation materials that we can use for many, many things, but we want to understand how the electrons move inside of these quantum materials. So an example of a quantum material is a superconductor. If you think of a normal copper wire that we use for transmitting electricity, copper wires are very inefficient. They lose energy in the form of heat and other forms when electrons travel from one place to another. We'd like to have wires that have perfect efficiency, and that's what superconductors are. The problem with superconducting materials is that they only function at really, really cold temperatures. And what we need to do is develop these materials that they function at room temperature in order to be useful in our daily lives. And so this huge beamline is used to study these very, very small superconductors. And the way it's done is like this. We take the superconductor, the X-rays, we're going to shine the X-rays on the superconductor. They come from that tiny pipe back behind me. The X-rays and the sample go into this vacuum chamber right here to my right. The X-rays will scatter off of that superconductor into this long arm behind me. The scattered X-rays will go all the way down to the end to that detector, which is down there. This detector can then move along this rail, and so we can measure how the X-rays scatter as a function of angle. And when we measure how the X-rays scatter as a function of angle, it allows us to understand how the electrons are actually moving around inside that superconductor. Well, we've made it all the way around the synchrotron ring, and we're back to the NSLS-II lobby. So that concludes our tour. Thanks for watching.
Thanks, Lisa, and hello again. Now that you've seen what's inside, you might have some questions. So we've gathered a group of scientists that work at the NSLS-II, and we'll be streaming them to you starting now. This is a live online discussion, so be sure to join in and ask your questions. Enjoy!
Children of all ages, welcome to the first virtual Summer Sundays here at Brookhaven National Lab. This is the first one that we're presenting, and this week's Summer Sunday will be about the National Synchrotron Light Source II. I'm Matt Whitaker from nearby Stony Brook University, and I get to work with a lot of amazing scientists here at NSLS-II. And we have 5 of them on our panel here today. We have John Hill, who is the director of the NSLS-II. We have Sean McSweeney, who is the Structural Biology Program Manager. We have Tiffany Victor, who is a postdoctoral science associate here at NSLS-II. We have Dan Olds, who is a pair distribution function Beamline scientist. And we have Andy Barber, who is a CSX Beamline associate scientist. So now that you know who all of the players are going to be for the day, we're going to start things off with a little bit of an introduction about who each of these people are and what they do now. And the way we're going to introduce them is by putting 2 sentences up onto the screen. And one of these sentences is a true fact about them, and one of them is false. So you can go ahead and take about 10 seconds to figure out which one of them you prefer, whether it's true or false. But first, I'd like to talk a little bit about John Hill. Again, he is the director of the NSLS-II. The 2 statements that he provided for us are, John holds the world record for balloon tossing, and John walked away from a plane crash. Now, as much as I'd like both of those to be true and somehow combined in a very weird, visually appealing way, I'm guessing only one of them is. So, John, take it away.
Hi, Matt. I'm John Hill. I'm director here at NSLS-II. Out of those 2 statements, the true statement is I was in a plane crash. Flight from Zurich to London, Heathrow, landed at Heathrow, was taxiing, hadn't got to the gate. We're all sitting there with our belts still on, and a plane went behind us and clipped our tail and knocked the tail off our plane. So it was a little unusual, but not too scary. We just had to sit in the plane for a while before we were allowed to deplane and get off and leave all our bags on the plane while they did all the security stuff. But that was the plane story. The balloon toss was a bull-faced lie. That's not me. But in fact, my son holds that record. He holds the record for the largest balloon toss. So that's me. Happy to be here.
Very cool. I was kind of picturing like a slow motion walking away from a big explosion in like a background with like, serious movie effects and everything. But that's
not
really
quite
cool.
That dramatic.
All right. All right. So next up, if I could, I'd like to introduce Andy Barber, and she has 2 statements for us as well. The first one is, Andy enjoys her job because every day is different, or Andy enjoys her job because she's not required to interact with people. Now, I don't know about you guys, but if this were me, both of those would also be true again as well. But Andy, if you'd like to let us know which one of those statements is true, and tell us a little bit about yourself.
Yeah, my name's Andy Barber, and I'm a scientist at the NSLS-II. I studied chemistry in school. But the thing that is not true is I really like my job because I get to work with a lot of different people, and it's required. So every day isn't different. Every day is different, and that's what I love the most. It's sort of my dream job. But to be really good at that, you have to rely on expertise from all kinds of people, like technicians and engineers, safety people, our administration. And also the users that come to do science. So it's really important to be able to interact with all of these people. And it's fun, so that also helps. Yeah.
Yeah, that's cool. People like me, so I apologize in advance for any problems that I might cause you. Next up, we've got Sean McSweeney, and he has 2 statements here for us. One of these is true, and one of these is false. The first one is, early on in Sean's career, complicated chemistry questions involved 5 atoms, but now they deal with hundreds of thousands. or the other statement is the first structure that Sean worked on took a team 5 years to solve. So, again, either one of these could be true to me. So, Sean, you're going to have to let us know which one is which.
Hi, Matt. Thanks. I started off my career interested in fundamental chemistry. I studied physics and chemistry, and I was interested in how atoms interact, how gas molecules interact to cause reactions to happen. This was way back in time when the ozone layer and the hole in the ozone layer had been discussed. So I was interested in upper atmosphere chemistry. Via a series of twists of fate and going to work at a synchrotron, I eventually started working in biological systems and found what I really enjoyed, which is biochemistry of proteins and the building blocks of our cells and our matter. And these are enormously complicated molecules which have amazing control over the chemistry that helps us function. And so today I spend my time looking at how these molecules interact and how they work within our bodies. So I'm guessing that means the other one is false. Do you want me to talk about that?
Yeah, sure.
So the other one is one of the first protein structures I actually tried to help solve. It's an enzyme which is involved in one of the metabolic pathways that helps energy be created in our body. And it didn't take us 5 years. It took 15 years to solve the structure. Back in that time, you had to be really very brave or stupid to try and solve protein structures because you were going to spend a large chunk of your career working on one enzyme or one protein and not getting very far very quickly. What helped a lot of that change is technology, and in particular synchrotron technologies and the types of beamlines that we're now able to make, including the ones we have here at NSLS-II, which are amongst the best in the world for doing this.
Very cool. So your false statement was actually an underestimation, which is definitely not the direction that I was anticipating it to go. So that's very cool. Next up, I'm going to bring up Tiffany Victor, and she has two statements here. Again, one is true and one is false. The first one is she was bitten by a shark while in the ocean, and the second one was she once walked in the crater of a volcano. And I was kind of hoping that she was bitten by a shark while walking in the crater of a volcano, but I guess, again, they're two separate statements. So, Tiffany, go ahead and let us know which one's real and which one's not.
Hi, Matt. Thank you. A virtual welcome to all of our viewers. Like you mentioned, I'm a postdoctoral research associate at the lab. My true statement is that I did walk in the crater of a volcano. Now, just to paint the picture correctly, this was not an active volcano with lava and ashes spewing out. And it's actually the remnants of a volcano that erupted several thousands of years ago on the island of St. Lucia, which is where I'm from. I did, however, also get bitten by another fish, but not a shark.
Was it a goldfish or something larger?
About the size of a goldfish.
Oh, yeah. All right. Excellent instincts. As a geologist, I appreciate that very much. So I unfortunately have not had the chance to walk through a crater of a volcano, so you get a lot more cool points than I do. Moving on next, we have our final panelist, Dan Olds, and he has two statements as well. Dan used to get paid to lie underneath plants and fields and count bugs for science, or Dan used to get paid to dart and track hyenas in the grasslands of Africa for science. Again, I really, really wish both of these were true and somehow combined. But Dan, go ahead and let us know which one is the true statement and which one's false.
Well, sure. So before I tell you which one, I'll tell you a winding story, which is really how I got here to NSLS-II. You may find a lot of us, Sean mentioned this, but a lot of us kind of start in one direction and then turn. And if you're wondering how do you become a scientist, how do you end up doing this? This was not even a job I knew existed when I was in high school, let alone college. It wasn't really until I got into my graduate studies that I even learned about this. My studies really, and I knew I wanted to go into science, but I was kind of like really into everything. And I tried out high energy physics. I tried out zoology. I tried out entomology. I tried out chemistry, and I finally ended up doing my PhD in condensed matter physics, but theory, and now I do experiments. So I think that there are if you are one of those people that's just like kind of into many things, there are pathways where you end up in these big facilities that you didn't even know you were going to. To that end, it is almost that both of these statements are true. However, I was not paid to dart the hyenas in Africa. I did that for free. So.
I was going to say that was my hobby. Actually, I just pop up and dart things and disappear back into the bushes. Yeah. Very cool. Well, it's really good to have all five of you here today. Hopefully we're going to have some good discussion. One of the things that I wanted to bring up really quickly is that we are, hopefully you're watching this right now, we're streaming on YouTube, Facebook, and Twitter. We're also accepting questions from the audience from all three of these sources. So if you have a question that you want to ask one of our panelists, please feel free to enter it into whatever source you're watching it from, and we will hopefully field some of those questions a little bit later in the discussion. But for now, we're going to move on to the next portion. We do have some true or false statements that are designed to kind of educate the public about what goes on at these synchrotron facilities, in particular at the NSLS-II here at Brookhaven National Lab on Long Island, New York. So the first of these true or false statements I'm going to get to right now, and that statement is NSLS-II is a gigantic X-ray microscope. We're not going to give the answer right away, give people a chance to think about it. Go ahead and if you want to, we'll take the sort of a audience participation poll on the social media platforms. If you think it's true, go ahead and give a thumbs up. And if you think it's false, go ahead and give a smiley emoji, or however the kids do it these days. I don't know. I'm aging myself out of this very quickly, obviously. So yes, the statement again, NSLS-II is a gigantic X-ray microscope. So let's see, which one of you do I want to pick on for this? John, I think you're first up. That's part of the perks of being king.
Thanks, man. So shall I give the answer?
Yeah, go for it.
So I would say that was true. We are a gigantic X-ray microscope in many ways, actually. Let me take the gigantic part first. Certainly it's a very big facility. It's about 2/3 of a mile around. So those of you who watch the video, you'll have seen people literally cycling around the building to get from one side to the other. It's that big. It was a big project to build it. It took us about 10 years from start to finish. It cost about $1 billion to build. That's another way, which is a large thing. It takes about 350 people to run it. As Andy already mentioned, people of all different backgrounds and skill sets to run it, all from scientists, engineers, technicians, safety, business. We have all that to keep us up and running. It's an X-ray microscope. So think about a microscope uses light, what we call visible light, to image things. And so you see, cells or something like that when you look in a microscope. We use X-rays to image things. So just like a microscope, you might focus those X-rays down onto something that you're looking at. But the advantage of X-rays, unlike visible light, is you get much more information out about the thing you're looking at. So we don't just see an image, but we might see how the atoms are vibrating in that sample that you're looking at. Or you might see how chemistry is happening or how electrons are moving. You get much more information you could ever do from a visible light microscope. So that's what makes it so interesting to use X-rays, because of the collecting all that different information. The other thing I might say is it's not one microscope, but in some sense it's sort of 30 different microscopes. We can run 30 different experiments all at the same time. So you might think about the ring, which is the center of the building, as being the light bulb, shining light down 30 different microscopes. Each microscope is maybe 100 meters long, something like that, and it's looking at something different about whatever it is you're looking at. And we look at all kinds of things here. I know some of the other questions coming up about that, so I won't go into that too much. The other thing I want to mention is that we built this, Brookhaven and DOE built this microscope for other people to use. I mean, this wasn't our own personal property. It's what we call a user facility. That means we built it for users to come and use. And people come from all over the US and indeed all over the world to use it because we are the best in the world right now. Many of the things that we do. John mentioned that in the context of the biology. We have some superb biology beamlines here. But many of our other beamlines are literally setting the standard for their technique. Best in the world, and that's a really fun place to be and really important place to be. And so as a result, many people come to use us. We would have probably had about 2,000 people coming this year, 2,000 different people to do experiments with COVID hadn't happened. We may get to talk about COVID later on, I'm guessing, so I won't go into that now. But yeah, I would say the answer to that is true. We are a gigantic X-ray microscope.
All right, very cool. So I just want to point something out before we move on to the next true or false statement. If you're watching this on one of the social media platforms, please type T or F for true or false instead of putting in emojis, because apparently I have no idea how this works, and I was just informed that what I said was incorrect, so I wanted to correct myself there. Okay, so moving along to the next true or false statement. The second one is NSLS-II only supports research on Antarctic plants and animals. Only Antarctic plants and animals. All three of them. Only those. So go ahead and type true or false into the chats that you have available on Twitter, Facebook, and YouTube. And I think I'm going to give this one to Tiffany.
Thank you, Martin. So that's false. In fact, if you were to walk the experimental floor during regular operation and you ask users what they work on, I'm pretty sure that you'd get at least 20 or so different responses. NSLS-II supports a wide variety of research that range from energy and material science to planetary science and even cultural heritage. That means at any one time you could have a user working on materials like batteries or microelectronic processors, looking at the structure of a virus, or inside of a rock or paint. You get the point. Not only that, but we could also look at processes or chemical reactions happening in real time. For example, a battery charging or discharging. And all of that is really important, which makes NSLS-II such a unique facility in that we could support such a wide array of research and researchers of such varied research backgrounds.
All right, very cool. Yeah, that's one of the things that makes working at Brookhaven Lab and the NSLS-II in particular great, is that you do run into people from all across different variety of backgrounds and scientific disciplines. So it's very, very cool. All right, I'm going to move on to the third statement. This true or false statement again, type T or F in the chat windows that you have available. NSLS-II can be used to study the basic building blocks of life, like cells and proteins. So if you think it's true, go ahead and type T. If you think it's false, go ahead and type F. And to answer whether this is true or false, I'm going to turn this one over to Sean.
And hi, Matt. The answer is it's true. We study the basics of building blocks of life through looking at individual proteins. We have a suite of beamlines which are set up to do this very well. There's a long history of this type of research at Brookhaven National Lab, including some very significant developments which have led to Nobel Prizes in this research. Increasingly, as we've understood better individual proteins, we're looking at how they interact with each other and how they form within the cells that make up our bodies. And so we've been developing more advanced techniques to complement what we do on some of the beamlines, to bring in more imaging, to see the cells in their totality, to see the interaction of all the molecules within the cells, and to see the cells as parts of tissues, such that we have a holistic picture of what's happening in biological systems and in life itself. And so NSLS-II has started to make a big contribution to this area, and as we develop further, I'm sure we'll make a very significant contribution to our understanding of biology for health, and also for understanding the basics of what makes life life.
And this is particularly right up your alley. So this is, I'm glad that I picked the right person to answer it, because I'm always nervous that I'm going to pick on the wrong person and be like, no, it actually should be them, or whichever Brady Bunch box you're looking at right now.
It's the reason I left the beautiful French Alps to come to Long Island, was the impact of what we could do here at Brookhaven Lab.
And the nightlife, of course. So
I'm old now, Matt, so anything after 9:30 is a struggle.
Yeah, I hear you. 3 kids makes that the same thing going on here in this house as well. Yeah. So, all right, I'm going to move right along to the fourth true or false statement that we have available here. When scientists talk about energy materials, they mean granola bars and energy drinks. So is that true or false? Again, type T or F to represent your answer in the chat on the social media functions. And I think I will turn this one over to Dan to give us the correct answer.
So here's a little secret about beam time that you may not know if you're not a user of our facilities. When you come and you're doing experiments on the Beamline, you're spending not hours, but often days sitting at this giant complicated machine doing science that you have been waiting months or years to do. And you're not getting a lot of sleep. You're sort of collaborating with other scientists who are helping you, and you'll take turns, maybe going back to the hotel and getting a couple hours of sleep here and there. But in this scenario, snacks are critical. Okay, like the proper snacks, the proper munchies are so important. And they say people eat bad over the holidays. You got nothing on beam time. All right.
Yeah.
So candy, cookies, granola bars, energy drinks. These are all standard, and so much coffee. But we don't talk about that. So that makes this question false. When we're referring to energy materials, we actually mean materials that go into devices like batteries, solar cells, capacitors, and catalysts. These are all technologies that are, whether you're familiar with them or not, right, extremely relevant to the lifestyle that all of us have really become accustomed to, which is that of cheap, clean, safe, plentiful energy, hopefully moving more and more to the cheaper and cleaner as these technologies advance. So it turns out that for a lot of these material systems out there, including those related to energy applications, the favorable properties we're looking at for, such as the ability to hold a charge or convert light into electricity or perform specific chemical reactions, are tightly correlated with things that are happening on the nanoscale and the atomic scale. For instance, solar cells need to convert light, right, photons coming in. Photons are neutral, right, that they don't intrinsically have a charge, into flowing charge so that we can power our houses and cars with them. Other materials that we might consider energy relevant, batteries are a super obvious one, right? Supercapacitors for the next generation of electric cars, filtration systems for exhaust from combustion engines, stronger materials for wind turbines, hydrogen fuel cell materials, safer ways of creating nuclear power, and ways to clean up and upgrade the older ways we used to do a lot of these technologies that maybe weren't so safe or as clean, so it won't be a problem for future generations. So if we want to be realizing all of these future technologies, there's a number of challenges in our way. There's a couple bottlenecks and things we need to solve today before we can get to that sort of like future we all really want. And as we dig into it, it turns out that the barrier to realizing most, if not the majority of this future tech, is that material science. And that's where we come in, right, at the NSLS-II. Whether it's X-ray diffraction, scattering, spectroscopy, imaging, tomography, you name it. We have, John mentioned, we have 30 different microscopes. We have all these different beamlines that we can use as tools to help foster discovery in these energy materials.
Very cool. Good explanation. And I would also like to point out that in the snack front, wasabi peas. Wasabi peas are key because when you start to feel tired, you take a handful of those wasabi peas, you'll be awake for at least 2 hours again after that. No problem. So
yeah,
definitely
I'll take
stick
your
with
word
those.
for it.
Absolutely. All right, so we're going to move on to our next true or false statement. The NSLS-II can be used to study strange phenomena in materials such as superconductivity. Now, is that true or false? Put the T in the chat if you think it's true, F in the chat if you think it's false. And coming full circle, we'll come back around. And Andy, if you want to answer this one and let us know which one it is.
Yeah, sure. So superconductivity may be a term that you might not hear about in high school. So usually, second year of college is where most people start to hear that term. And it basically means being able to conduct electricity without any resistance. And for that, if you've ever like used a vacuum cleaner or a toaster or a hair dryer even, and you touch the cord that's made of copper or metal, which also conducts electricity, you will see that cord is very warm. And that's because the electricity flowing through encounters some resistance, and some of that electricity has been lost and converted to heat. So you can imagine like building up the power grid with the copper wires leading from the power source all the way to our individual houses. It would be great if we could get 100% of that electricity to our homes. And so that's where superconductivity comes in the future. But it's being used right now. So if you go get an MRI in a hospital, it uses a magnet that relies on superconductivity. So it's very important now. And lucky for us, the NSLS-II can be used to study superconductivity. We look at it many different ways. So sometimes superconductivity can be measured by understanding how electrons travel through a material and sort of the energy that they need to maintain flowing through this material. And so we can do those measurements. We can also theorists also describe superconductivity through different kinds of methods that rely on indirect measurements. So we have a different microscope for that. And then additionally, superconductivity can be observed in materials that exhibit other properties. And so we can understand how electrons order before they become superconducting. So the answer is true, and we're lucky that we have many different instruments that we can take and interrogate these materials in different ways to build a complete and holistic picture to help physicists start to understand how superconducting works and how we might be able to make devices of the future.
Very cool. And we're going to turn it over to some audience questions right now because we're getting a lot of them in through the various social media platforms. So we want to make sure that we get some of your questions answered. And actually, one of the questions that was most recently asked, Andy, it refers directly to what you were just talking about. So I'll start off with you if that's all right. What is currently the highest temperature for attaining superconductivity?
So it's certainly above 120 Kelvin, which is above a liquid nitrogen temperature. I think maybe 150. There are some room temperature superconductors that can be made, but they're very difficult to use. But the vast majority are around 120 or 150 Kelvin. So for that to make sense, you can think about that as minus 240 Fahrenheit. So the use of these things sort of on an everyday kind of application in our homes is a little far off. But that's why it's important to study them and understand how it works. And just to get a perspective of what minus 240 Fahrenheit is, you can think about the moon and on the places on the moon where the sun does not shine. And that is about the temperature that you would need to have these things in order to use them.
That's quite cold, colder than we normally achieve anywhere regularly on here without performing some sort of scientific technique for it. All right, so we have another great question that was submitted by the audience. This question, John, I think I'm going to direct this one to you. What instruments are used in the different experiments or the 30 different beamlines that are available at the NSLS-II right now, and who designed them? And where can we learn more about the instrument's design?
Okay, good question. There are, as we said, sort of 30 different instruments around the ring. They're sort of evenly spaced around the ring, roughly, and each one has a different instrument at the end of that beamline that's using the X-rays in perhaps a slightly different way to carry out whatever experiment they plan on carrying out. Most of those instruments were designed in-house using a mixture of commercial parts that you can buy from specialized suppliers and our own designs. So that's a collaboration between the scientist who knows what they want to get out of that experiment, the engineer who knows how to make that work physically, and the designer who can put that together in the drawings. So it's a mixture. There's usually at least some customization because we're trying to push what we can do beyond what anyone else has done before with these instruments. So we might, for example, let me pick one beamline, which is what we call the NanoPro beamline. That focuses the X-rays down to a really small spot, about 10 nanometers across. Just to convert that, that's 30 gold atoms. So these are really tiny X-ray spots. They're the smallest in the world. To focus that beam down requires you build a lens to focus the X-rays down. That itself is a very complicated, difficult thing to do. It took us 5 years of R&D to build the first lens that get us down to that kind of level. So that's a sort of scientific in-house piece of equipment that we have built here at NSLS-II, the lens. Then you mount it in a set of stages to transition it, to translate it around, move it, position it in exactly the right place. Some of those you can buy. We have in-house engineering that puts those together in a very stable, temperature-controlled environment. So I'm trying to give you a picture of how complicated these instruments are. And like I said, it's a mixture of our own staff putting these together with commercial designs. You asked where you can get more information. All of our beamlines have a website on the web page. It's a public web page, so if you go to bnl.gov and look for NSLS-II, you'll be able to find the beamlines there. And each one of those has a little bit of information about their instruments on those web pages.
Very cool. The website has a lot of information that can answer a lot of questions that we might not have enough time to get to today. So be sure to use that as a resource if we don't have the opportunity to answer your question. Next question that we have up. I am fairly familiar with X-ray diffraction. What are some other beamline techniques and how do they work? So, Tiffany, I know that you work primarily in areas other than X-ray diffraction. So if you could say a few words on this.
Yes, Matt. So besides X-ray diffraction, I do X-ray imaging and X-ray spectroscopy. Like X-ray diffraction, the setup is sort of the same, where you have X-ray light coming towards your sample and then a detector that's placed behind it. In X-ray imaging, it could either be directly behind it or perpendicular to it, and so the type of information that you receive is different. So in the case of imaging, what you have is a raster scanning, so your sample is moving, and you get this visual picture of what your sample looks like or the chemical makeup of it. So you learn about elements on the periodic table that are in it. So for example, calcium or sulfur. And if you wanted to know more about the chemistry, then you could perform an experiment like spectroscopy. So you could find out what oxidation state, say, let's say an element like iron is in, whether it's 2+ or 3+, or what types of other elements that it's bonded to.
All right, very cool. Okay, so I'm going to move on to the next question that we have here, and that is, are the samples destroyed during the testing? So maybe Sean, can you take that one on?
Sure, this is a good question, and I think the answer depends on what is your sample, because to answer the question, you have to decide whether the sample is physically robust to the effect of the X-rays it hitting your sample, so you can make the measurement. In terms of the science that I do, the answer is a very categorical yes. We have such high flux densities, flux powers, that the lifetime of one of our samples in the beam is of order seconds. And so it presents us with very great problems, because we have to either collect data very fast before the sample is destroyed, or we need lots of samples in order to piece together from little fragments of a data set, a complete data set. Little bit like taking your page, ripping it up into 100 pieces, throwing it in the air, and then putting it back together so you can read, your homework for tomorrow, that sort of stuff, or what your lecturer has set you. So we have that problem. We try to get around it in different ways. But what we've seen, I think, around all of the beamlines now is NSLS-II has pushed synchrotron science, the light sources, into a new field that areas of science were previously. They thought their samples were immune to the effects of the X-rays, are now finding that they're seeing problems because the sheer flux of the X-rays is so high that it's damaging the sample as we measure it. And this is a real problem and something that needs a lot of research. In fact, and don't let me ramble on too long, but previous place I used to work, we saw a similar problem. there's been a group of us who've worked together over 20 years now to try to understand the basic physics and chemistry of what's happening when you illuminate biological molecules with X-rays. Because there's an awful lot of interesting chemistry and physics that happens when you bathe a biological molecule in an X-ray beam. And over a period of, as I say, more than 20 years now, a group of us have worked to try to understand these so that we can, these effects, so that we can apply them to data collection. Importantly, so that when we get a picture of what we're looking at, we know it's not contaminated by the effects of the damage that we know is being caused by the X-rays. This is a really important topic, a really important subject for me and for all my colleagues here, and something that causes some head scratching at all of the instruments around NSLS-II right now.
Yeah, and all of the instruments at all of the synchrotrons around the world, like you had said, everybody experiences some degree of this as well. So it's definitely a very important question.
Yeah.
Okay, so I'm going to go ahead and move on to the next audience question. This was brought up by a couple of you so far, and one of the people who hasn't brought it up is Dan. So, Dan, you're the person that I'm going to target with this question now. What is the difference between an engineer, technician, an inventor, and scientist? Because all of these different classes of people have been mentioned as being part of the science that goes on at the NSLS-II. So can you talk a little bit about the different types of people and the different backgrounds that come together to make this happen?
So, yeah, this is a great question. We are absolutely a big science facility. It takes a lot of people with a lot of different expertise to make things work. So, on paper, you might say, well, the scientist is saying, this is the science I want to study. Like, I'm a material science. I want to know more about batteries. I want an instrument that can study batteries in the way I want to study them. And then an engineer might work with the scientist to design it. And then once the entire thing is designed and built, right, the technician is helping the science to actually do the things that need to happen, swing the wrenches, that kind of thing. Is there a fourth one?
Engineers, technicians, inventors, and scientists.
Yes, and maybe so something needs to be invented to realize the sort of scientist dream. But that is only where it sits on paper. The truth is that we're all kind of doing these roles very, very interchangeably, right? I am right in with, I may have the designation scientist, but I'm also helping design and swinging wrenches, and my technician might officially be my technician, but my gosh, if I won't rely on them for their instincts and their insight, and we all kind of come from different backgrounds. We all, it's not like you pick one of these tracks and necessarily go down it. And these are absolutely huge team efforts where, regardless of your title, all ideas go on the floor and everybody works together. But in principle, there's also some breakdowns of scientists are generally have masters or PhDs. Engineers have some kind of formal engineering training. But, as soon as I lay one of these rules down, you're going to find cases where it's not true. So, in essence, it's a big team effort. And we all do different roles, and we all have important parts to play in the facility. But we're all there working on the beam lines and with the end goal of trying to help make discoveries happen.
I'll just add, I think Dan said it really well. It's definitely a team effort. As I mentioned at the start, there's 350 people it takes to run this facility, and certainly all those different skill sets are required to make it work. The only thing I'll touch on is the inventor one that you mentioned, Matt. Is in some sense, I think all of us who are working here are inventing. We're all trying to create something new that no one's ever done before, and that's the technician, engineers, scientists. We're all rolling it together. That's what it makes it fun for me, at least, is doing that creation, doing something new that no one's done before. And a place like NSLS-II, that happens every day on every beamline. It's really fun.
Yeah, that's one of the coolest things, just being as an outsider, as a scientist from a local university who gets to work with the people and with the science that goes on at NSLS-II. It's very cool to see so many different people from so many different backgrounds coming together to attack the same issues. It's definitely a unique and exciting place to be.
I want to add one more category of person. So we have the business office, the HR office, things like that, but the computer scientists are crucial now in ways that they would never were before. And so that's another category of people. You might call them engineers, you might call them scientists. They also exist as a kind of boundary, and it's there. The data science now is a big part of what we're doing. So it's not just the physical hardware anymore; it's the data side of it. And that's like I said, a new thing for us. Maybe the last 5 years it's changed, and so that's another group to keep in mind. If people are listening, thinking about what they might want to do in the future, that's another career path that could end you up at a place like NSLS-II.
All right. That's actually a question.
All of this is true, but people look fairly worried when I pick up a spanner, a wrench. So I try and speak not English, but
if you got the name right, they'd be less worried, Sean.
Maybe in 10 years' time.
It does take a while. I'm from upstate New York. Moving down here was definitely culture shock. I can't imagine what it must be like coming from across the pond. So, moving on real quick to the next question. John, you're on the block again for this one, if that's all right, since it was specifically addressed to you by name. How did you plan a project that took 10 years for completion, given the fact that you're working on constructing a state-of-the-art facility? What do you do if things start to become obsolete?
That's also a great question. Well, so I wasn't even part of the project back then, started 10 years ago. It's a very large effort, collective effort. So you sit down with a big team of people and start to dream about what might be possible in 10 years' time. You look at the state of the art as it is at that time. You make your best guess about where it's going to go, and you slowly evolve things through. At some point in a big project like that, you have to draw the line and say, okay, this is what we're sticking with. This is the technology that we've got, and we're going to build it relative to that. And so that happens maybe 4 or 5 years into the project. That's when you baseline it, as it's called. You fix everything. You say, okay, now we're going to build it. So you try and future-proof it to the extent that you can. I mean, we designed this facility to continue to grow long after it was finished. So you heard us say a few times today that there are 30 microscopes on the floor now. We have room for 60. Those next 30 could use new technologies that we didn't know about 10 years ago, and certainly will use new technologies. We're continuing to innovate and build on what we've already got. The data science, as I already mentioned, has come leaps and bounds beyond what was before. So we can run detectors much faster, or we are running detectors much faster, higher resolution. So things are changing all the time. So yeah, you try and stay on top of it. You build what you can. As I said, I used to know the number of man-hour or the people hours that were put into the facility. It's hundreds of thousands of hours collectively to build the facility. And so it's a large team constantly trying to innovate and stay on top of things.
Yeah, absolutely. And a lot of that work is still going on. Even at the beamlines that have been completed, they're constantly undergoing a state of evolution and upgrade, and it's a never-ending process.
Yeah.
So I have one here that's particularly relevant for the point in time that we're in right now, and I think Sean is probably the best suited to answer this one. I know that the NSLS-II ran through the lockdown earlier this year to support COVID research. So can you discuss a little bit about what it was that you were doing during that time and what you were looking for there?
Sure. This could take me more than half an hour if I really get into a flow, so don't worry about stopping me. So
let's go with an order of magnitude less. So.
Okay, I'll give it a go. So as we know, this virus is infectious and is easily transmitted. We worked from March through to now, essentially without interruption, to try to find ways of dealing with this virus. How do we do that? So the best way I have of trying to describe how we did that was, if you think about sports, think about any sport. You want to know what the team consists of, what are the players, what are the major players, how do they interact, what are the strengths and weaknesses of each of those players, and how can you devise a strategy in order to stop them doing what they do well, in order for you to be able to combat and overcome the team so that you win. In a way, the studying this virus is the same sort of concept, in that the virus itself is relatively small. There are only a few dozen components to this virus, which use our cells to hijack our cells in order to replicate. So what we've done is strip it apart so we understand each of the players, study those players computationally so that we have detailed analysis of their similarities and dissimilarities to previous viruses. And then we've been looking at ways to interfere with the virus's infection and the viral process so that the virus can't replicate in our cells and therefore be transmitted and make us sick. And we do that using a technique called protein crystallography. So you isolate the individual molecule from within the virus. If you do it just right, you can make this form a crystal. This is very soft, very tiny crystal in most cases. And then if you do the experiment just right with X-ray diffraction and a degree of mathematics, you can understand the structure. And that gives you a starting point for a basis of understanding how that particular part of the virus performs its function. And then the next task that we've been working with extensively, both within the consortium within the national lab system and within the DOE and with external partners, is to find molecules which will stop the function. Often people think about proteins and their function as a sort of lock and key mechanism, in that you need the right substrate, the key, in order to lock or unlock the protein's function. And this is the way in which we've studied protein function for a long time. But what happens if you can make a key which fits, won't be released, and blocks the molecule's function? Then you've got the starts of a way of defeating the replication cycle of the virus, and you've got ways of stopping the virus reproducing itself. And so we've been doing a very intense effort with a lot of groups to try to find these molecules which will stop the infection or stop the process of making new viruses. And we've been doing this on all of the different targets using a big range of techniques. And we start to see some success. We're looking at more complicated examples as we've learned more about the processes. And ultimately, I think that what will come from this is that we'll have a range of antiviral drugs which will help inhibit and slow down infection and transmission of the disease, as well as ultimately vaccines to be able to treat us against this type of disease. And lots of that work will be based upon the information that comes from understanding the structural elements that the virus makes itself. And so I think when we have a chance to look back on this and reflect a little bit what we've done, we'll see that NSLS-II has made a very significant contribution to the understanding and to the treatment of this viral pandemic that's keeping us all in our own rooms and not together and things like this.
If I might add a couple of things to Sean's. First of all, the technique he's talking about, in order to study these proteins, he has to grow crystals, which is a big bottleneck in drug discovery. And what we do well at NSLS-II is produce these very bright beams of X-rays. We talked about those a few times. That means on Sean's beamlines, he can look at crystals 200 times smaller than you can anywhere else in the world, which saves when you're trying to grow these crystals in the first place to discover if these drugs work or not. That really shortens that bottleneck in terms of the drug discovery route. So that's really important. That's one of the things that we're really good at here. And just to put this in context as a whole, 93% of all drugs the FDA approved in the last 15 years were solved at a synchrotron first. That just tells you how important synchrotrons are in drug discovery generally. And it's almost certain that the drugs that get discovered that fight COVID come from a synchrotron. Hopefully NSLS-II, but who knows? We're part of the fight, at least. And so I think that makes us all feel very proud of what we do here, knowing that we're part of that fight.
Yeah, it's very cool, and it definitely an application to what's going on in society today. So the NSLS-II is once again one of the world-leading places for doing this kind of research. So that's definitely awesome. Right here on Long Island, New York. So the next question that I have, I just want to see a show of hands real quick from the people who are on the panel, which one of you knows about the SIX beamline? Anybody? All right, perfect. So, John, right. Andy, I'm going to send this question to you then real quick. The last beamline shown today in the video, which was the SIX beamline, can someone be in the room while it's running?
Yes, so that's true. That's partly because we have soft X-rays at the SIX beamline, which means they're not high energy, so we don't need a lot of shielding to protect people. If it was at a different beamline with a higher energy X-rays, then the answer would be false. But 6 is very lucky in that you can go into the room and you can see this big long arm move around. And hopefully that will happen in the next year, that it will just move around continuously. Yeah.
Very cool. Now, the same may not be true at all of the rest of the beamlines, which leads to one of our next audience questions. Are your X-rays dangerous? And if so, how do you protect people in the labs? Dan, I'm going to throw that one at you.
Are they dangerous? Inherently, yes. You would not want to walk in there and sit in front of an X-ray beam. Are they, do I feel safe working there? Absolutely. I've brought my kids there. We have so much shielding in place. Shielding is a very, very big part of what we do. We have a lot of safety and interlock systems. So X-rays themselves cannot get into an area where people are also, because of the, if I want to go in and into my hutch, which is where we do the experiments, and say to change out a sample, I need to sweep the hutch, a series of alarms happens, there's a very extensive closing and locking up procedure. All of the sort of like safety protection systems for people are very separate from everything else. I can't accidentally do something wrong and put myself in a dangerous situation. So this is a sequence of shutters, keeps things closed. Really an extensive amount of engineering went into ensuring that these beamlines can operate very, very safely. And from that standpoint, right, I wear a dosimeter around all the time that monitors my dosage, and it's never read anything. So I get a greater dose of radiation when I walk to my car in the parking lot than I do sitting at my beamline.
Yeah, it's a very good point.
Because of the sun. Not because
right.
we're exhausting X-rays or something. Let's just be clear.
Right. Excellent clarification. I've got one more audience question that I want to take really quickly before we go back to some of the really cool true-false statements that we have prepared. The question that was asked from the audience is, are we doing research related to meteorites? Tiffany, you want to say something about that?
Meteorites.
Mm-hmm.
So I don't think so, but John could.
Yes,
I'll leave it for John to answer.
The answer is yes, Tiffany. I know of a few experiments that have happened at NSLS-II looking at meteorites and also these things called interplanetary dust particles. Oh, Matt looks like he knows some answers too. So maybe I should turn it to you, Matt.
No, I wasn't suggesting that, but I was just saying that, some of the experiments that I've been involved with over the last couple of years have also been looking at meteorites
as well. The experiment I was thinking was...
I should have known that then.
The experiment I was thinking of was a NASA mission to collect dust particles from outer space. A mission called Stardust that collected them in a satellite and then brought them back to Earth, and they were studied at NSLS-II. And these are particles that left over from the very early formation of the solar system. And so looking at the minerals in those tiny little particles allows you to tell how the solar system was formed, whatever that was, 10 billion years ago. But Matt, what are you up to?
Well, some of the research that I've been involved with at some of the imaging and microscopy beamlines at NSLS-II are actually looking at meteorites that have fallen to Earth and seeing what mineral phases are present in them and what the chemistry of those things are. And that helps us kind of understand the building blocks of planets in the universe, or in particularly in our solar system, to see what's going on out there that we can't see here on Earth. So it's a very cool place to be because a combination of different beamlines at NSLS-II gives us a whole load of information on these interplanetary materials, which is very cool. So, good question, and hopefully I gave at least a decent answer compared to everybody else on the panel who's much more qualified than I am. So, right now we're going to go ahead and go back to a couple more of the true-false statements that we had prepared. I will, move right along to the next one. The next one that we have ready and available is the NSLS-II has a fully functioning particle accelerator to create the ultra-bright light. So if you think that's true, go ahead and type T, and if you think it's false, go ahead and type F in the chats. And in the meantime, I will turn it over to John to give us what is the correct answer here.
So the correct answer, Matt, is yes. So the way we generate the X-rays is we use electrons to generate the X-rays. So the electrons first come from, you can think of it like a light bulb, a filament that gets hot, and when it gets hot, it gives off some electrons. And we take those electrons and we take them through a series of accelerators. Some of them are linear accelerators, so that's a straight line. They put into a circular accelerator, boosted up to the full energy, and then put in the main ring, which we call a storage ring, where they are stored. They keep circulating around that ring. They have an energy of 3,000 million electron volts, as we call it. So that's a difficult unit to think about in everyday units. But if you took one electron and crossed it, say, across a battery of 1 volt, you'd have to do that 3,000 million times to accelerate up to the energy that we're using. At that energy, they're relativistic. They're moving pretty much at the speed of light as they go around the ring. They'll live in the ring for several hours before they would decay, drop out. So we put more energy in to kind of keep them in place. And as they go around that ring, we take them through a series of magnets. And those magnets are designed to do several things. First is to squish them into really tight beams. That's really important because the smaller the electron beam is, the brighter the X-ray that you're going to get out at the end. So NSLS-II was designed to do that really well, really small electron beams, and that was the accelerator physicists that was their big contribution, was thinking about how to do that, and building that accelerator. And then we take these beams of electrons and we pass them through arrays of magnets. So you think about a north-south, north-south, north-south magnet, maybe 3 meters long, something like that. And as the electrons go through those rays, they get wiggled back and forth because they go through the magnetic fields. And if you do that just right, they give off X-rays as they get wiggled back and forth. And those make up the beam that we use. And Einstein's special theory of relativity says that beam is compressed into a very bright beam because these are relativistic electrons. And so we take that beam of X-rays and then we take them down the beamline, deliver them to the sample, and carry out whatever experiment it is. So the heart of the NSLS-II is the accelerator, producing those X-rays in the first place.
Very cool. That's a better explanation than I've ever heard before, so thank you very much for that. So moving on to the next true or false statement. During the COVID-19 pandemic, NSLS-II had been closed and no research had been done at all. I think we already kind of addressed this one, so we should all type the right answer in the chat. But Sean, if you want to reiterate real quick what the answer to this one is.
I was going to tell you the wrong answer, Matt, but I decided to not go with my demon. The answer, of course, is false. And I told you a little bit about the crystallography experiments that have happened throughout MinSafe and the pandemic. In addition, we've been looking at scattering experiments, looking at proteins and other macromolecules in solution so that we can look at the shape as they interact in solution. We brought up some other beamlines to look at different aspects of chemistry and imaging of materials associated with dealing with the pandemic. And on top of all of that, we continued construction of a new facility, a new laboratory we've been bringing up called the Laboratory for Biomolecular Structure, which uses imaging through the use of electrons in order to study more complex materials that we can't crystallize, biomaterials that we can't crystallize, as the name implies. And we've opened that up to research for COVID-19 now, and we expect to have that as a fully functional facility through the fall. So the answer is a very definite false. All
right, cool. So this next true-false statement relates a little bit to the energy materials discussion that we had earlier. But NSLS-II's X-rays help scientists to see what's going on inside a battery while it charges and discharges. Is this true? Type T in the chat. Or is it false? Type F in the chat. And this one is going to be fielded by Dan.
So let's banter a bit while they think and answer this difficult question. Matt, how long does the battery on your phone last in an average day before you need to charge it again? If you're like hardcore Netflix in it or something.
Oh, Netflix. Okay. Yeah, I was going to say it depends on whether or not I'm using Facebook or Netflix, but if I'm not, it can last almost 2 days. If I am, about 26 minutes.
Yeah. Okay.
Yeah.
That's how mine, my phone's dead right here. I would love for a better battery in a phone. I dream of a world where I only need to charge my phone like once a week, instead of every day, or really what is multiple times a day. When I first got this phone, it could live a couple days between charges. A couple years old now. It's really, the electronics on it are fine, the camera's on it's fine. It's the battery, right? That's not behaving. It's not healthy like it used to be. So this statement is true, right? As we've already covered. Batteries are absolutely something we look at NSLS-II. But what is it that we're looking at? So it turns out that the reason batteries work or over time not work, especially these batteries, have to do with happening on the atomic scale often, right? You can have engineering failures, but if the material's going out, it's really at the nano and atomic scale. As we've heard, synchrotron X-rays can be used to study down at those very small, right, all the way down to interatomic spacings, right? Angstroms is a unit we use on my beamline, right? 1/10 of a nanometer. So this is important if you're studying how atoms are arranging, how they're accommodating each other, what sort of a local environment they have. So you've all heard probably of lithium-ion batteries. Lithium is this screwy little element on the periodic table way up in the corner. Behaves very strangely, but we've found great use for it. It's small, it's mobile. So we design these batteries, lithium-ion batteries, right? It's not just a chunk of lithium. In fact, it's a lot of carefully constructed chemistry and material science to give little homes for the lithium to live in when it's charged up, and pathways for the lithium to travel out when the battery's in use. And then when you recharge it, right, you want the lithium to go back in. And so it's this motion, this atomic scale infrastructure and nanoscale infrastructure that is critical to battery operation. Now, over time, these little highways, they get into disrepair, right? The homes crumble, things don't work as well, it doesn't move as well. And yeah, exactly. We want to study this. We do study this, in fact, all the time, where we're trying to understand, in order to fix this problem, exactly what's happening down there at that nanoscale, that atomic scale. How are those pathways breaking down, or even in cataclysmic failure, right? What is happening to cause, the failure of these battery materials? And specifically, we do study them as they charge and discharge. We set them in the beam, and we look at them, and we monitor what's going on, and try to look for those failure modes so that those discoveries can help lead to new, better solutions so that we can get to my dream of a week-long battery or a month-long battery for my phone. So yeah, statement's true.
All right, cool. Very good explanation. We'll move on to the next statement really quickly. NSLS-II can be used to study brain cells. So is that true or false? Go ahead and enter your option into the chat, and I will call on Tiffany to answer this one.
So that one is definitely true, Matt. In fact, one of the research areas that my group looks at is Alzheimer's disease. Specifically, we look at what role metals play in the development of the disease, so metals like copper. And we look at postmortem brain tissue, so no live subjects, or we look at animal models of the disease. And we take it to the Beamline and we do imaging on it to get a visual idea of how the copper or the metals are related in these plaques or protein aggregates in the brain tissue. We also look at things like blood vessels that sort of look like spaghetti. And we do some spectroscopy to see what kind of chemical states those metals are to try to get a better understanding of the role that they play in Alzheimer's disease.
Oh, that's very cool, and definitely societally relevant research direction too, which is very good to see. One more quick true or false statement before we go back to the audience questions to round out the rest of this Summer Sunday edition. Magnets are the only materials that cannot be studied with NSLS-II. Now, is that true or false? Again, type T or F in the chats, and I will turn this over to Andy to answer.
So I'm sure, Matt, you were playing with your magnets on your refrigerator earlier today. And
it's how I communicate with my children.
Right. And you notice when you get them two oriented just right, one will push the other one across the table without actually having to touch the one that's traveling, right? That's a really cool property of magnets. We don't study those kinds of properties with magnets. This refrigerator magnets, it's a very special kind of ordering that we have in magnets, and there are many other kinds. So the answer is false. We do use NSLS-II to study magnets, just not necessarily these bulk ones that we see on refrigerators. But you can imagine that if you took a bunch of these magnets that you have on your refrigerator, basically, and arranged them in a tile pattern like you would on your floor in your bathroom, and then shrink that down to a really small size so that the magnet itself, one of them is about 1/4% of the human hair. These are the kinds of samples we're studying now. So it's this little magnet pattern. And that can be studied at a couple of different beamlines. These things are called artificial spin ices or nanoarrays or magnet nanoarrays. And they're important to understand how they work on this nanoscale to make really small logic devices. Right now, logic devices in your electronics are still fairly large, much larger than sort of how memory is stored. So this is one way we can start to reduce the size of our electronics even further, is making smaller logic devices. Another kind of magnetism that we study in NSLS-II is sort of out of this state of, two magnets, where they either slam together or they push each other apart. There's sort of gradations and how the material interacts. And if you've seen a weather map of a hurricane and how sometimes the meteorologists draw arrows, and you can see these arrows are circulating, you can think of this as a way physicists represent this sort of strange magnetic phenomena. These materials are called scorpions if you want to have a look at them, but they're used in potentially for quantum computing. And quantum computing is really exciting because we can condense information in even a smaller amount of form because it's not a yes or no. It's sort of an in-between sort of state. So you can more richly describe information in a smaller area. But these are all things that are far in the future that we need to first understand the physics of before we can start building them for people to use.
All right, very cool. Now we are in the last couple of minutes of this Summer Sunday program. So unfortunately, there are still more questions than we're going to have time to get to, but there was a really poignant question from the audience that I'd like to have all of our panel members answer, if possible. And that question is, if you had to pick one experiment that you've been involved with at the NSLS-II that you are the most proud of, what would that experiment be? And who do I want to pick on for? Dan!
So this is actually a really hard question because we've done a lot of things. I will say that my favorite experiment that we've done is a study of these so-called molten salt materials, which are promising materials for safer nuclear power. And it was just an extremely fascinating study where we had to get the heating just right. We wanted to be heating this thing up to 800 degrees Celsius and watching what is effectively a salt form and melt as it heats up. And then as we cooled it, watching it recrystallize. What I do is a technique called powder diffraction. I want to look at things that are powders. We cooled it so slowly at one point it formed a giant single crystal of salt, which was not great for our detector, but was just a very fast. It was like, oh yeah, physics. Like that's like it happens, and you're like, yeah, okay, single crystal growth. But the data out of that was so beautiful. We generated gigabytes and a terabyte worth of raw data, and we had to make these really cool new methods to sort through and look at that data using machine learning and artificial intelligence and really dig in, because there was so much data from this experiment, you couldn't get it all in a conventional way. So it was kind of the combination of the cool sample environment and the cool data and then the cool methods we used to analyze it. I'd say that's my favorite one we've done so far, but there's so many cool upcoming ones. The future is bright.
Nice. All right, let's see. I'm going to go in the order that you appear on my screen. So, Sean, do you have an answer for this one?
Gosh, I was sat there thinking maybe you give me a few more minutes. Okay. That is a really tough question, as Dan said, and in some ways the easy answer is the experiments we're going to do next month or next year, because we'll have learned so much more. I think the experiments I'm most proud of seeing and being involved with are the very first ones we did after the years of building the beamlines, of getting them to the point where they'd started, of getting to a position where we could actually start doing something with the X-rays we were producing, across several beamlines. Because as John said, it takes years to get to this point. It's an awful big team works on this, a lot of effort, and then those first experiments let you see the potential. Yes, we've done this right. Yes, there's a lot of work to go, and yes, it's going to be exciting in the future. And I think those are the experiments I'm most proud of, because we got there as a team, stayed as a team, and continued to work as a team and develop the facility like that. That's where I am on that question.
Very cool. Andy, do you have a particular favorite?
I do. But I don't know if it necessarily qualifies as an experiment in the traditional sense. So the reason why I knew a little bit about SIX was I was lucky enough for the last 2 years to be participating with that team and helping that instrument become what it is. And so the day that we were able to prove that we had sort of this very high energy resolution after 2 years of working on weekends and holidays to make the instrument as good as it could be was probably really exciting. That was the most exciting thing, and especially for the scientists that are responsible for that instrument now, because of the science that it enables in the future. So the reason why it was important to get this world-leading energy resolution with world-leading flux is we can very quickly do experiments that are not possible until this beamline was built and commissioned. And so now the scientists and users that use that beamline can start to understand and measure things that previously weren't measured before, and with the resolution to say this theorist is right or this other theorist is right. So it's really at an important time in, I guess, our history where we start to understand how these quantum materials actually behave and how we can theoretically describe them in order to make new materials of the future.
Very cool. How about you, Tiffany? What do you think?
Let's see. So I think my favorite experiment is some X-ray tomography that we did on some E. coli cells. We spoke a lot about the 2D imaging, but tomography is the one where you get to see a 3D representation of your sample, which is really cool because you don't just get one slice or one view, but you get the holistic information of what you're looking for. And the reason why it's one of my favorite experiments is because we were able to obtain really high spatial resolution. Earlier on, John mentioned that the nanoprobe is able to focus down to a really spot size of, let's say, like 10 nanometers. And so we were able to get a spatial resolution of less than 30 nanometers, which is really, really tiny. Not only that, but the technology driving the experiments, using one type of protein to click onto the protein that you're interested in seeing, and using these X-rays to see where it lights up. So it tells you where exactly the protein that you're looking for is. And that's really important because right now for X-ray microscopy, we don't really have a lot of those types of proteins. And so it's very important for others who do biological type imaging.
Oh, that's very cool. Now, John, I feel like it might be a little unfair to have you answer this question as the director of the entire facility. So I think I have another question that is equally as important, but that would be more targeted directly to you to close us out. Would that be all right with you?
It would, but I was gonna comment a little bit on this question because I thought it was a great question, and because I'm the director, I don't get to take part in any experiments, so it's an easy answer. I don't have an experiment that I'm most proud of. What I'm most proud of, though, is what you've just seen on the screen. Everyone at NSLS-II is part of something really special. They're all doing something that you can't do anywhere else in the world. And as I walk around the ring, and one of the real shames about today is we can't be showing people in person what's going on the floor. You're just seeing it through us and trying to convey through our eyes. But if we could get you out on the floor as we did last summer, and hopefully next summer again, we had 1,000 people walk around the facility, and then you could really show each beamline, you could see what's going on. And in each place, we're doing something amazing. And that's what I'm really proud of. The team we have here is amazing. Set of experts doing things that you can't do anywhere else. And I couldn't possibly pick one experiment that I'm most proud of, but there are so many coming out of the facility. It's really, really wonderful. So that was going to be my answer. I can't pick one child of them all, but they're all my favorite.
Right. Exactly. The last thing that I would throw your way then is, how is the NSLS-II unique to light source tools that are available at other national labs? What sets the NSLS-II apart?
All right, so several things I would say, and then maybe others can chime in. But so we're one of the newest facilities, newest synchrotrons in the world, and we designed NSLS-II to be very bright, which means producing lots of X-rays in a small spot. So we do that really, really well. When we were first built, we were the brightest in the world. There is a couple of facilities that are just beginning to be upgraded now that might come similar to us or a little bit brighter than us. So brightness is one thing that we have going for us. The other thing I think we have going for us is diversity in some sense of X-rays. We haven't really talked about this in this forum, but we don't just produce one type of X-ray. We produce X-rays over a very wide range of energies, which you can think of as wavelength, all the way from the far infrared, which is a very, very long wavelength, very low energy, all the way up to hard X-rays. And that's something that's really special about NSLS-II, is you can go around and find an experiment that uses exactly the energy of X-ray that you want for your particular experiment. And I think that's one of our real strengths, is that we have the ability to do something very well across that wide range of energies. So that's really our niche, I would say.
And the people. I'll give you guys props. There's a lot of good people at NSLS-II.
Absolutely, no question about that.
So I am getting the high five signal or high sign that we are just about out of time. So if I could just take a moment really quickly to thank everybody on our panel for joining us today. And especially I would like to thank all of the people who are out there in the internet land viewing this. Hopefully you had a chance to either get your question answered or learn something new, or at least had a good time watching us. I know that things are a little bit different, but today is a good day to be inside watching a live stream of something, because apparently the weather is non-cooperative for many other things. So we thank all of you for joining us here today for the first of the virtual Summer Sundays here at Brookhaven National Lab, and be on the lookout for information for other sections of BNL that will be having their Summer Sundays in the near future. John, if you want to say anything to close us out.
Just thank everyone watching for your participation. It was great to have a chance to talk to you all directly. Like I said, hopefully next year we get you in person. I want to thank everyone on the panel. You guys were great. And Matt, you were fabulous. Really nice job. Thank you.
Thank you very much. I appreciate that. So, again, if you did not have a chance to have your question answered today and you'd like to send more in, please go ahead and send an email to liveevents@bnl.gov, and we will do our best to get you the answers to the questions that you might have. In the meantime, be well, stay safe, and thanks again for joining us for Summer Sunday.
Thanks. Bye-bye.
Bye-bye.